I am pleased to introduce Timothy Dolch. Timothy is Associate Professor of Physics at Hillsdale College. After receiving his Ph.D. from Johns Hopkins University, he held postdoctoral positions at Oberlin College and Cornell University, both with the North American Nanohertz Observatory for Gravitational Waves, collaboration. In Nanograv, he chairs the Education and Public Outreach Working Group. He is also a research scientist with Eureka Scientific Inc. Primarily a transient radio astronomer, his research focuses on pulsars and using them as tools to detect gravitational waves from merging supermassive black holes. With Hillsdale students, he constructed the low-frequency all-sky monitor and on-campus radio telescope. Professor Dolch is a member of the Society of Catholic Scientists, and the title of his talk is The Search for Extraterrestrial Intelligence, an Overview. Let us welcome our speaker.
Thank you so much. I want to start with some definitions here. We've heard a lot about the situations in which perhaps signs of life could be detected, and those are what I'm going to refer to as biosignatures. Biosignatures are just signs of biological activity. They could be in our solar system, they could be on exoplanets, anything that's the sign of active life. Technosignatures is now the preferred term for what is often called SETI, the search for extraterrestrial intelligence, because you can only do a detection if there's technology to detect. And those are signs of technological activity from intelligent life. Those could be intentional. They could be extraterrestrial analogs of the famous Arecibo message that was sent out by the now former Arecibo Observatory, may she rest in peace, if you saw the news about the collapse of the telescope in December. But it famously sent out some of these messages. That would be an intentional one if we received something like this. Those could be call signs, signs of intelligence, or they could be actual encoded messages like the Arecibo message. Technosignatures could also be totally unintentional. They could be waste heat from technological activity. They could be unintended radio communications. People have done the calculation. Earth military radar could be detected at interstellar distances with a large enough radio telescope. And those unintentional ones might contain or not contain symbolic information. So in this talk, I'm going to focus on the possibility of receiving technosignatures from remote sensing. I'm not even going to talk about the possibility of analogs to things that we've sent out, like the Pioneer plaque and the Voyager record. I'm also not going to talk about sending messages any further. This is about receiving them, the possibility of that. Now, the larger context is the field I work in called Transient astronomy. And to be clear, I don't do SETI research myself, but everyone who works in the field of transient astronomy, also called time domain astrophysics, in one way or another searches for time-changing signals from objects or phenomena in the sky. So people who do that do tend to rub shoulders with people who actually do technosignature research. Transient astronomy is looking for things like flashes or bursts, phenomena in the universe that go boom. And those are often detected from large-scale sky surveys. So when you have large amounts of images and time-based information, you tend to detect stuff that you didn't expect. Transient astronomy is quite old, centuries old. Supernovae, exploding massive stars when they run out of fuel, have been known for a long time. That's a form of transient astronomy. Gamma ray bursts, many from merging neutron stars, are also transient astronomy, as are pulsars, and that's my own field. I work with the North American Nanohertz Observatory for Gravitational Waves, called Nanograv, receiving pulsar signals. Pulsars, as I'll show you in a moment, are pulsating radio stars, and we do this in order to use the pulsars as tools for another kind of astrophysics, to detect gravitational waves from merging supermassive black holes. That's not what I'm going to talk about. You can ask me at the coffee break, but that's the context in which I have gained some familiarity with what's happening in the technosignature world, because there is some overlapping membership in our collaboration, and those collaborations that do technosignature searching and some shared telescope instrumentation. Okay, but a classic example of transient astronomy that started to touch on the possibility of technosignatures was in 1967 when Dame Jocelyn Bell Burnell was doing a sky survey, and she detected something that she called scruff, which is this stuff here. But upon further examination, it was pulsating on and off. Boy, that sounds kind of artificial. And it was, for a few months, informally, kind of facetiously termed an LGM, a little green man. However, at the time, the theory of stellar evolution was becoming very well understood. And it was well understood that massive stars end their lives in supernovae. And the remnants of those supernovae are very, very dense stars, about the mass of the sun packed into a 10-kilometer diameter radius, that have very powerful magnetic fields, and that results in beamed radio emission, and those that happen to point to the Earth pulsate on and off, just like a lighthouse would. So, in fact, it was not an LGM, it was a pulsar. So there are a lot of phenomena in the universe that at first glance appear artificial. And transient astrophysics encapsulates quite a few phenomena. More recently, there's a phenomenon called fast radio bursts, and these are single millisecond long pulses that come from other galaxies. So it's a hot time in astronomy for these things, and those fast radio bursts are of natural origin. They're not understood exactly yet, but it's something that a lot of research is going into. But in general, if you're searching for transient events, thinking here and there about technosignatures as a possibility is a natural outgrowth. You're used to expecting the unexpected. This is a paper that I recently worked on, which was on the pulsar side of things. And this is one of the ways that I've just rubbed shoulders a bit with the technosignature world. In this paper, we used a mathematical technique that happens to be called cyclic spectroscopy to process pulsar data, and you can extract a lot of information with this technique. This is a map of the pulsars you could use it for. And in writing up that paper, I realized that some of the people who do technosignature searching were also using this mathematical technique, so it had some applicability there. I ended up citing their papers and reading them in the conclusion of that paper. So there's some overlap. Additionally, this is our on-campus radio telescope at Hillsdale College in Michigan, where I am, and it's called the Low Frequency All-Sky Monitor, Station 5. And we built this, students and I together built it 3 summers ago. We had a lot of fun doing it. Later that year, it turns out there was a review paper on the topic that mentioned that our telescope network, all 5 stations, were actually something you'd want to look at in the panoply of observatories that look for technosignatures. So that was exciting. I didn't know that when we built it. Finally, you might have seen in recent months, since last December, there were a lot of popular articles on a emphasis on candidate signal. And it turns out that a student at Hillsdale College who worked with me on the monitor telescope did an REU, Research Experience for Undergraduates, the following summer with Breakthrough Listen, the group that does a lot of technosignature searching now, and he was actually the discoverer of this candidate signal, Shane Smith, and here he is. He's a rising senior, and I advised his senior thesis, which was another version of that paper that's been submitted to Nature Astronomy, so I got to read it ahead of time. It's not published yet, but I can tell you that if there was something really exciting there, I couldn't tell you because it's still embargoed. But more seriously, there is a long history of candidate signals, and this is like a lot of them. So I'll get to that later. Now, there's a long history of searching for technosignatures. I could talk for a long time just about that. A few highlights here. In 1896, just shortly after Hertz discovered radio waves and Tesla started experimenting with them as communication means, Tesla himself started thinking about using them to receive signals from Mars. And similarly from Hertz, Kelvin, and Marconi. And it got to the point that Tesla and Marconi both claimed to receive some signal. Now we now think that was one of many natural radio signals that are out there. And the real turning point, though, was after the birth of radio astronomy, which started in 1933 when Carl Jansky first detected our own galaxy's natural radio emission. In 1959, Cocconi and Morrison, the Philip Morrison who worked on the Manhattan Project, wrote the seminal paper about this. And they did some calculations about what you might look for. Here they are. The following year, Freeman Dyson published his paper about what we now call Dyson spheres. If there were a megastructure blocking a star, you'd see an excess of infrared emission, given the star's luminosity. In 1960, just after the invention of the laser, a paper with Towns on it, one of the inventors of the laser, the following year was about the possibility of detecting laser pulses from extraterrestrial civilization. So that's when this started to flourish. 1961, Frank Drake, here he is, started to undertake the first sky survey looking for technosignatures at the Green Bank Observatory. And at a conference at Green Bank Observatory, he tossed out this equation, which wasn't the most serious equation ever written down. He didn't intend it that way, but it's what people now call the Drake equation. And it's a way of estimating n, the number of technologically advanced civilizations in the Milky Way that we might be able to detect. And there's a lot of factors in here, a lot of probabilities that determine that n. And as we've seen in previous talks, all we know is that n is greater than or equal to 1. But the equation is supposed to give you an idea of the uncertainties that you deal with. What we now can say, though, is that at least compared to some estimates in the 1960s and afterward, it's certainly clear, because of the great number of exoplanets we know now, that the fraction of stars with planetary systems is quite high. And we also know, as we heard in Chris's previous talk very nicely, that at least prebiotic molecules are not rare in the universe. They're throughout our solar system, they're in giant molecular clouds. So some of these factors might be higher than you think. But still, all we know is that n is greater than or equal to 1. So if you're going to look for these things, for some sort of sign of intelligence, where would you look? And traditionally, and to the present day, typically narrow-band signals are looked for. These are signals at a particular frequency, not spread out over the radio spectrum. And that's because with a narrow-band signal, that's how you can carry a lot of information at a low energy cost to the producer. That's why we use them for communication. So where on the spectrum would you look? The radio spectrum is quite large. And going back to that original 1959 paper, you might want to think about some key frequencies. And these are, to take a term from game theory, Schelling points. And Schelling points in game theory is a classic example where you're in New York City and someone else is that you want to get in contact with, but you have no way of communication. How do you meet this person if you both intended that? Well, you might meet at Grand Central Station, or you might meet at the Empire State Building. You wouldn't just sit in a random sandwich shop and wait for this person. So people have applied this thinking to the radio spectrum where you might look. There are several natural radio frequencies that are of interest. 1420 megahertz is where hydrogen emits a narrowband emission. It's a very famous line. It's how we map out hydrogen in the galaxy. People thought about, what about that times pi or divided by pi, something intelligent sounding. The frequency of positronium has come up. The peak frequency and higher frequencies of the cosmic microwave background. But the part of the frequency range that's been of choice is 1 to 10 gigahertz. And that's for the following reason. If, and this is the big if that we've seen in previous talks, if the other civilization is like us, well, perhaps they would be from another Earth-like planet with a lot of water looking out. So their window of the radio sky would look similar to ours, where at lower frequencies you have the galaxy's natural emission, which gets brighter and brighter, would block any signals. And you go higher than about 10 gigahertz, and your own atmosphere starts to block your ability to receive radio signals. So if they're like us, that Schelling point kind of thinking, well, 1 to 10 gigahertz is the range. And if you're used to thinking about water, well, there's hydrogen and there's the hydroxyl molecule, the dissociation products of water. So that's often called informally the water hole, like a watering hole for animals. It's all just a guess. Fortunately, though, what frequency to look at is becoming kind of a moot point because now technosignature searches are very wideband. You're receiving numerous channels across the spectrum at once, and you can go back and analyze them later. So we don't really have to think anymore about what specific frequency should we use. What information would you look for? Well, back in that original paper, they thought about, would you look for a prime number sequence of pulses? Would you look for small sums of numbers, 1, 1, 2, 1, 2, 3, and so on? If you were to detect a signal, what would you look for? How could you possibly decode it if there were detected information? Lawrence Doyle et al. Has some interesting thought on this, of applying some of the methods that are used to analyze dolphin communication. There's something called the Shannon entropy, which is a way of showing quantitatively that there is information content to be communicated in a signal. Maybe that could be applied. So there's any number of things to look for. There might be nothing at all if it's an unintentional technosignature. But there's always limiting factors. There's radio frequency interference, RFI, from our planet. That's hard to look through, easy to mistake. There's also interstellar scintillation. This is from a diagram from Cordes, Lazio, and Sagan, 1997. And scintillation is a fancy term for twinkling. We see stars twinkle at night because we're looking through a variable density medium of our atmosphere, and that makes them flicker on and off from constructive and destructive interference. And the same happens at interstellar distances for point radio sources that we're looking through. So they'll fade on and off at different time scales. This is a map of the severity of that. By the way, this is not a dolphin up here. A friend of mine I showed these slides to said, it looks like a dolphin. You're talking about dolphins. Total coincidence. Total spurious detection there. What is often looked for in these searches is a Doppler drift narrowband search. Why is that? Well, we would look for narrowband signals, and if it's coming from a particular planet, which is what we would at first order assume, then that planet is always, being in its orbit around its own star, is always undergoing an acceleration with respect to us. So due to the Doppler shift, it's always, the received signal is always changing, is always drifting, because the source would be changing its speed. And this is from Sheik et al. 2019, and this is a detection of a technosignature from Mars. It's from one of our spacecraft there. And this is just a sanity check to see that the algorithms are working. And you can see there's that drift because Mars always has a tiny acceleration with respect to us. And one of the things that's making this field really intriguing is now that we know so many exoplanets and more Earth-like exoplanets in terms of the habitable zone, we can actually have a predicted range of what the slope of this line should be for a given planet. So that's one of the exciting things going on now. Now, there's a long history of different SETI projects. I don't have time to get into all of them, but many of them were conducted with the Arecibo Observatory and many other telescopes. But they were all very well thought out. They were, of course, all negative. There were lots of candidates. The most famous one is called the WOW signal, because it says wow there. The reason it says wow there, this was from the Big Ear Telescope at Ohio State, which is down here. It is now a golf course. But when it was there in the 70s, Jerry Amon, who was even then a volunteer observer, looked at the strip chart recorder. This is frequency this way, so these are narrowband frequencies. This is time. And at one frequency, something shot off the charts. Digits are the low numbers, and when you get to high numbers, it goes into the letters. You can see how big that was. And that's it. There's nothing else to say about it. It was moving with the sky like a point source would. People have gone back to look for repetitions. It never repeated. And that's it. What else can you say about it? And there's been a history of other examples, some of which turned out to be natural phenomena, and these are bonus scientific discoveries. CTA 102 is a variable active galactic nucleus. There's a supermassive black hole in a galaxy that has material falling into it, and it flickers from very large distances. In a Soviet SETI program, which was another elaborate part of the story, originally this was a candidate signal. It seemed to be turning on and off, but it was later understood from that original data that this was a variable AGN. Here is an image of SETI at home. How many of you in the audience had this screensaver in the 1990s and onward? Yes, and I was proud in college to have this on my computer all the time, and I reached the top 20 in the world briefly. But at the time, what it was a distributed computing network. You used it as a screensaver. When you weren't actively using your computer, it would receive some data, and it would crunch it and send it back to the SETI Institute. And this image here was an example candidate signal. There was a candidate and several others. This particular one from the Serendip project. And again, it was never explained, but it was consistent with some unidentified man-made RFI, radio frequency interference, and never repeated or anything. There was a similar one about 5 years ago from the Ratan 600 radio telescope in Russia that made the news, but again, nothing else you can say about it. And Breakthrough Listen 1, actually BLC1 is the term being used now, is another one of these candidates where, and just from looking at the articles in the news, you can see, whoa, that's pretty interesting, but it's difficult to say more about it. But there's a lot of exciting efforts going on right now. One of the eventual victories of the people who worked on this is that they were able to fund a dedicated telescope for this purpose. And this is the Allen Telescope Array in Northern California. And it was reborn several times after losing funding, but they just kept going. It's a very state-of-the-art instrument. And they've done some interesting things and put out some interesting recent papers. They've looked at specific exoplanets nearby and reported their non-detections. And they also spent a lot of time on that WOW signal spot in the sky and published their non-detections. But the really big thing happening is now Breakthrough Listen. And this is a project by Russian entrepreneur Yuri Milner. He has dedicated $100 million for technosignature searching. And there's a 10-year planned timescale. They started in 2015. And it's really pushing the field along to, I think, an exciting new level. There are currently 3 telescopes being very actively used. One is the Green Bank Telescope in West Virginia, 100 meters in diameter. The Parkes Radio Telescope in Australia is being used. You need northern and southern hemisphere coverage. And also, for optical SETI, the Automated Planet Finder at Lick Observatory in California. So they're looking for laser flashes. Breakthrough Listen also has agreements with many, many other telescopes in the world, either for future data or to analyze data that's already taken. I won't go through all these, but includes infrared searches as well. So this is a diagram from a recent Breakthrough Listen paper, Enriquez et al. 2017, and here is where they looked at nearby stars with exoplanets. And this is a non-detection plot. So what you see is every dot on here is a part of parameter space that was searched and reported as a non-detection. What's on the x-axis here is the power of a transmitter if it would be transmitting in isotropically, all directions uniformly. And this would be an extremely advanced civilization. And here on the plot is something the equivalent of Arecibo, sending out a radio pulse. The y-axis here is basically frequency of pulsation. So the lower down you go, the more rare the pulse would be. The more to the left you go, the dimmer it would be. So you can look at the history, recent history of SETI as moving these points down to the bottom left more and more. So as searchers are getting better, that's where it's going. This is from another paper by the Breakthrough Listen people, and you can see it's really cutting even lower every year into here. Now, the previous search was for exoplanets. This one is pointed toward the galactic center in an untargeted search, because there's been literature on this too. That's another Schelling point, is that you might want to, if civilizations in the galaxy want to somehow choose a direction, maybe the galactic center is the best. You have the highest density of stars in that direction. So that's, and that's been an interesting study, because what's been coming out of the recent papers are ancillary scientific discoveries. Bonus science that is not a technosignature detection, but it's other really cool science that comes out of it. On the left here is one of these fast radio bursts, one of these natural pulses from other galaxies that's not entirely understood yet, that was detected by Breakthrough Listen. So it's not that nothing is accomplished if you don't detect a technosignature. On the bottom right here are pulses from an object called the galactic magnetar, and this is a neutron star. It's like a pulsar, but much higher magnetic field and turns on and off in a harder to predict way. So they detected small pulses from that. Just last night, on the Astronomers Telegram mailing list, which sends out breaking news of stuff that in transient astrophysics that might not stick around, there was reported by the Allen Telescope Array a fast radio burst they detected. And there it is. It is fairly narrowband looking, but it is, this is a natural fast radio burst, because you can see parts, you can see a signature here that with time goes lower in frequency, and that's characteristic of these natural bursts. So they're doing good science even while making not the technosignature detection that, of course, would be the very best outcome. There are also efforts underway to look for vanishing stars or appearing sources. And this is the sort of thing you might expect from large-scale engineering along the lines of Dyson spheres. And this was a project by Beatriz Villarreal et al. And they pretty systematically looked for these things with the complete knowledge of all of the natural phenomenon that could look like this. And they ended up finding a list of candidate stars that vanished. Here's one from the 1960s. They went back to these old images and re-imaged them, and that star vanished. They don't think that this is a technosignature. They could be flares from M-dwarf stars. These are particularly flaring kind of stars, so there could have been an otherwise invisible star that just flared up here that's very consistent with this, or very distant and very red supernovae. So again, this is a bonus science discovery from these studies, but there's a citizen science project with it and plans for follow-up, so it's another exciting effort. Okay, so I'm going to conclude here with a few thoughts. Why do this? Is it a waste of time? It's a high-risk, high-gain game. It's difficult to assess the probability. Maybe it's higher than we think. If it's lower than we think, the lure that it would be the greatest scientific discovery in human history still makes somebody want to do it. And that appears to include Yuri Milner, which is great. And there's a lot of spin-off science. The SETI at Home software from the 1990s really popularized distributed volunteer computing, and now it's done with protein folding and all kinds of things. And of course, there are all of these ancillary scientific discoveries I've been telling you about that keep happening. So a negative detection is not a waste of scientific effort. Of course, the non-scientific impact would be tremendous on a philosophical and theological level. And a robust non-detection would also be very significant if you could argue more from an observational basis that we are alone. Sometimes people will say that's already happened, but I would argue that has not happened yet. I would argue that we are nearer to the beginning of answering this question than toward the end of where we would say observationally we seem to be alone. And that's because what Breakthrough Listen and other groups, they're not the only game in town either, what they're doing is really now informed by big data science and machine learning. What they do in a few weeks of observations is probably equivalent to decades of SETI before that. So I think now we're really observationally at the point where this question is first being seriously asked. And also the discovery of exoplanets. We now know habitable zone Earth-like planets, where to look. So I think if this effort goes on for decades, and more exoplanets are discovered, and there's targeted campaigns on all of them, and nothing comes up, maybe then you can start to say that's a negative answer. But we're definitely much closer to the beginning of that than to the end. What does this mean for being a Catholic scientist? I think of Father Sean's homily this morning, where he said that, he quoted Father Luigi Giussani, who talked about experience being the basis of Christianity, that the whole Christian adventure began because John and Andrew met this man one morning. It was an experience. And we can think abstractly a lot about this problem, or we can, and, as Jonathan also said this morning, have humility and step back, take the time, acquire the data, and let the experience guide us and be in that position of dependent humility instead. So I will stop there. Thank you.
Thank you so much. All right, we have a couple minutes for questions. Oh.
Thank you. So one of the things that I dearly miss in these talks is a little map that says, what distance are we probing now, assuming a civilization that can transmit at the level of, for example, the Arecibo telescope at the time? And curious to know the answer to that question. Also, of course, as we probe further and further out into the galaxy, we're looking for signals that have taken longer and longer to get to us. And so those civilizations are either dead now, or maybe they're so much longer lived that, let's say it was 30,000 light years away. Well, now they could transmit an even more powerful signal. And if we waited 30,000 years, we'd hear something, which is a sort of a depressing thought. But actually, I'll just ask, how far out have we probed, assuming a technology on the other end that's Arecibo-like?
Right, and thanks for that, Jonathan. And this is, so on the question of what would the map look like, it depends on the nature of the search, because there are very different search strategies. The ones that have searched stars, directions of stars with known exoplanets, those stretch out to hundreds of light years, and that map could be constructed. And then there are the untargeted ones that point toward the center of the galaxy, and those are harder to map because you're just looking toward the highest density of stars, and that's all you can say. There are also extragalactic searches. Maybe in an extremely advanced civilization, you could receive a signal from. So that's also been, that target list of galaxies is growing as well. As far as whether the civilization still exists, if you look at the Drake equation, the last term is one of the terms in there is the length of time the civilization exists in order to send signals. We don't know how long that is. Maybe it is quite long. Maybe once you reach a technological level, you stay there. Or as talked about in previous talks, maybe that's a brief flicker. Maybe, there's more nihilistic possibilities like extinction. Maybe civilizations go extinct, or maybe everyone decides that, the Amish have it right, and we, being a civilization without technology is more sustainable in the long term, and who knows? So I think that would depend on that number too.
On that note of destruction of civilizations and the fact that I'm from Los Alamos National Laboratory, I have to ask you this question. Would nuclear explosions on other planets be detectable on Earth, or vice versa?
That is a fascinating question. My first thought is probably not. If it were an individual explosion, there's one of the famous Soviet astronomers who was in the history of these searches, and this was mentioned in Simon Connolly Morris's talk, is the Kardashev scale. And there's Kardashev 1, 2, 3. These are supposed to be extremely advanced levels of civilizations. And the Kardashev 1 civilizations, which in fact is the limit shown here, would be a civilization that puts out a solar level of intensity across the Earth's surface. So basically, something that's lit up the surface of a planet has that level of technology. So maybe something like that you could detect.
Hi, thanks for the talk. I'm wondering if there's any sort of standard for claiming a discovery, like analogous to particle physics where you need a 5 sigma bump. I would expect for maybe a repetitive signal it might be easier, but for a single output like the wow signal, how would you even claim to have discovered something?
Thanks for that. Yeah, and that's a great question. Where's the benchmark where you really claim a detection? And yeah, generally, people have thought that it would have to be repeating. Again, if it's just once, what can you say about it? And it would have to. You would have to rule out every possible man-made source, and you would also really need long-term repetitions because of that scintillation phenomenon. It's really easy to miss some occurrences because sometimes it might be in a minimum. So if a signal were detected, it would have to repeat for many years probably before you would claim victory.
Do you happen to know if anyone in recent years has done a feasibility study to see if it would be possible to build a network sensitive enough to pick up domestic VHF communications, say 50 to 500 or 600 megahertz, where you might find television and high bandwidth voice that are domestic?
Right. So the question is how powerful of a telescope would you need to pick up the Arcturus 4 I Love Lucy? Right. That's yeah. Right, or the evening news. Right. It would have to be pretty big because you would need a radio telescope the size of the square kilometer array, the giant telescope in South Africa that's being built to detect military radar or Arecibo-like pulses from another planet. So it would be a telescope probably an order of magnitude at least greater than that in terms of collecting area.
Okay, great. Let's thank our speaker one more time.